Yeah, thanks, Garrett, for the introduction. So I'll be talking about ForceRay, and that is basically a force-controlled virtual thumb extension for ergonomic one-handed touch input. And I did this work together with Marcel Lahaye, Borchers, and Voelker at RWTH Aachen University in Germany. So many of us use a smartphone every day, and also a lot of people actually use it or prefer to use it one-handed. And that's often because we are occupied with the other hand. For example, we want to drink a coffee, we're holding on in public transport, we are carrying an umbrella while we are calling someone, or wearing a lot of shopping bags while at the same time we are looking on our iPhone or other device for the next shopping mall. When smartphones were introduced, they were actually pretty small, and that's pretty fine for a one-handed use. But over the time, the screen, which serves as both the input and output surface, has been growing in size. And now that smartphone manufacturers are even capable of reducing the bezel, these sizes increase massively. But there's a catch with that when we use it one-handed. So we usually only have the thumb available for input. And if we want to use the thumb for input, that's pretty much limited to where we can actually reach. So one solution to this problem, of course, could be to design the user interface in a way that it fits this ergonomic movement. So here's an example for a one-handed keyboard for a left-handed user using the left-handed thumb for text input. But there are also many situations in which we cannot really reduce the interface to that just because there are so many other components to be shown on the screen. So here's an example for that. There's someone who likes to take a picture, and you can see most of the screen actually is occupied by the camera view. But at the top, you can see there's an option for activating the live photo mode. So let's see what happens when the user is about to tap that target there. So it's almost unreachable. There's a lot of motion going on. The device is almost falling down. It's pretty unhandy and non-ergonomic. So in the worst case, what can happen, of course, the device can fall down, the screen can break, or we have a lot of thumb stretching going on and re-grasping back and forth. That can be pretty tedious and maybe even painful. But manufacturers of smartphones are aware of this. So for example, Apple has introduced reachability. So what you can do is you double tap on the home button or you swipe, and then half of the screen actually moves towards your thumb. But at the same time, 50% of the screen is not visible anymore. So there's a context loss basically going on here. Or Samsung, they introduced the one-handed mode. So you swipe from the corner, and then the screen shrinks to about 2/3, so that everything is more in place for the thumb. But at the same time, targets and labels, they're very small. It's hard to hit them precisely, and actually reading them is also difficult. But research has also looked into this. So one of the earliest works that looked into a reachability technique, actually for smaller devices, is MagStick. So what you do here is you basically drag the thumb towards the palm, and at the same time, there's an extension growing at the same length beyond the thumb. And then the targets are actually snapped to magnetically. But the problem here is that you need to reach at least at half of the screen to reach the upper part of the screen, and the bigger these screens become, the more difficult that is. A more recent technique is BezelCursor. So what you do here is you swipe from the bottom or from the sides, and you get a virtual thumb extension that grows depending on how fast you are scrolling or swiping. But again, what you can see here is that when targets are located at the top of the device, people tend to move the device and stretch their thumb, so it's also a little bit uncomfortable in that area then. So coming back to the part or area where we can actually do touch input. So the question that we had was, can we now actually make a fully reachable touch interaction only dependent on that small proportion of where the thumb can actually go? So we wanted a thumb-friendly, full-reach technology that also provides a stable use, so no shaking with your device, that at the same time preserves the whole context and does not need any scaling. And we also wanted it to be transient. That means we only have it active as long as we need it, but in all other cases, when we can reach the targets with the thumb, we can just simply use direct touch input. So we looked into one property of touch input, and that is force. And we think that force can actually provide these and satisfy these constraints. And we called it ForceRay because our thumb has now a virtual thumb extension that is controlled by a force. And here's how it works. So in this video, you can see the smartphone, and there's a collection of images that the user can select from But before to do so, he needs to select the select button in the top right corner. So with ForceRay, what we do is we place the thumb on the screen, and as you can see, nothing happens so far because direct touch input is still working. But when we apply a little bit of pressure, we get this virtual thumb extension. And now we can move our thumb and drag the ray that is crossing a particular subset of targets. So if we want to go to the select button, all we have to do is move the thumb to the right-hand side such that the ray crosses the select button. But as you can see, there are many targets actually crossed by the ray, so how can we communicate which target we actually want? And this is where force input becomes important. So we just press, and the more we press, the further the cursor moves along the ray until we are at our wanted target, the select button. So now the question is, how can we confirm that input? That's a little bit tricky with force input. So because when we remove the finger, the force drops, and so would also the selection drop and select a different target. So what the user has to do here is quickly lifting the thumb off the screen, and our system can detect this such that everything works perfect that way. However, the timing here is very, very important, and I will talk about that later. So now let's say we want to select some of these images here. So let's say the burger icon that has already been selected here, but we can also see that there are other images that we can select. It's just moving the ray and then just letting the thumb go, and then we're there. So we wanted to understand how does ForceRay perform, how can users actually work with it, and therefore we conducted a study. So participants had to select a bunch of targets. We limited that to a total of 12, so there are a lot of distractors that people could select, but they should not select. But there's also a small proportion of the screen that is only a distractor, basically meaning that it looks like targets, but they cannot be selected, because in this area we suppose that direct touch input would be the way to go. We also classified these targets into two groups. One is the border targets, and we think that these targets can be reached very quickly because the user just has to steer the ray until it crosses that target and then apply as much force as possible, which is super easy to hit the target. But for all other targets, there are other targets on the ray before and after, so we need a really careful force control here. So we wanted to compare ForceRay against classic touch input, then the Samsung one-handed mode that we call the shrink mode because we just re-implemented it, then MagStick and BezelCursor. And in the first place, we were interested in the time and the success rates that users had, but also a little bit about the ergonomics. So what does the thumb actually do, and how is the device held in the hand? So here you can see an example of the user using ForceRay. We had two different target sizes, a small and a large one. And here you can also see this is already a more trained user that can do both placing the ray and controlling the force at the same time. So it's not like the split step that we've seen before. So looking at the results, we could see that what we expected, that classic touch is still the fastest input to go, but it has a lot of problems with the device stability. But BezelCursor and also ForceRay then were already next, and MagStick was a little bit more taking time because people had to carefully think about where to place the thumb such that they could reach the outer targets. And for the shrink mode, the animation that communicates the user what's actually going on, how the UI is shrinked, also takes a little bit of time. Success-wise, Classic Touch was less successful, and also MagStick had the problem that not all targets could be reached, and in the shrink mode, targets were partially too small to be hit correctly. But for BezelCursor and ForceRay, we had more than 95% accuracy, and these differences were not significantly different from each other. So let's have a look more into these two techniques. So we wanted to understand where does the problem come from, the time difference that still exists between BezelCursor and ForceRay. And as we can see, this is mostly due to the inner targets because it's more difficult to control them more precisely. But for the outer targets, there's no difference between the two techniques in time and also in success. Both of them are equally working well. So looking at the thumb movement, what we saw is that for BezelCursor, people still do a lot of thumb stretching. But for ForceRay, the whole thumb movement is in a very comfortable area that moves around the thumb's joint. And since the users were sitting and in a stable environment, we also captured the device rotation, so basically the sum of device angle changes. And what we saw is that these angles were very small for ForceRay, but were much larger for all the other techniques. And that was true for the x-axis, also for the y-axis, and most prominent for the z-axis. So now we wanted to understand if people can become a little bit better in using ForceRay when they train the technique, because we've shown in a paper last year that training makes people better in controlling the force. So we recruited a fresh set of participants, and they trained the two top techniques for us. So there was ForceRay and BezelCursor for 12 different sessions split across 4 days. And in total, I think about more than between 1 and 1.5 hours of just selecting targets. So what we can see is that, yes, they became faster, but it was true for both techniques. So both ForceRay and BezelCursor users were about 200 milliseconds faster afterwards. And for the selection accuracy, for BezelCursor, it was more or less constant. For ForceRay, it decreased in the end. And that was because people were more trained to lifting the thumb much quicker than they did before. And the timing of the thumb lifting significantly affects the way of which target is actually selected. So if people use ForceRay on a regular basis, if they become experts, you might need to recalibrate the timing of thumb lifting to interpret which target the user wanted to select. So what can we now take away from this? So I'm not saying that ForceRay is the technique that you should use for daily smartphone interaction. If targets are reachable, and that's often the case for targets like the one-handed keyboard, then go for classic touch input. It's fast and people understand it very quickly. However, if the targets are located beyond the thumb's area, but still are large enough, then the shrink mode can be a vital alternative. And you can also reduce this animation time for experts because they will understand what's going on in the UI. But if they are too small and more located at the borders, let's say for menus, then ForceRay can be a very good alternative because users are very quick in reaching those targets. Or if ergonomics and stability are very vital, as we've seen, there's almost no device motion going on, then again ForceRay would be a good pick. But otherwise BezelCursor is also a very good and especially the easier to learn technique. So let's get back to our initial example, somebody taking a picture, now with ForceRay. So all that the user needs to do is press and move the ray to the live photo icon or button, lift the thumb, and as you can see, the device is almost not moving, so the viewpoint is basically stable. However, ForceRay has also some limitations. So as we have seen, there were only right-handed users, and we also only had right-handed users in our study, and that is because ForceRay is dependent on the handedness. So for a left-handed user, you can see that the origin of the ray that extends the thumb is located in the lower left area. And also, if targets are further away and we move the ray, then the problem is that there's a larger drift from target to target than when the targets are closer to the thumb. So for future work, we would like to go beyond simply tapping and also look whether we can do a reachability technique for swipe and scroll gestures. Also, we want to look at the effect of walking, because walking significantly affects the user's force input control, because we apply some inadvertent pressure when we are holding the device in our hand. And I think that a hybrid version of BezelCursor, where you basically start swiping, but then when it becomes too uncomfortable to stretch your thumb, you can then use ForceRay to extend the cursor even further, would be a very cool and interesting technique. So this concludes my talk. So I've talked about ForceRay, which is an ergonomic thumb extension for one-handed smartphone input. It has almost no grip change and almost no device rotation going on. And with a little bit of training, users can select targets in about 1.4 seconds. That includes all the targets that we had, so the border ones and the center ones, with 96% accuracy. So I'm done, and thank you very much for your attention, and I'm happy to take your questions.
Okay, so we have time for a few questions. Remember to state your name and your affiliation. Thanks.
Hi, I'm Gerard Laput, currently at Carnegie Mellon University. Really great work, nice presentation. I think this is a really promising technique. You mentioned reachability on iOS. I wonder if you actually use that as a comparative baseline for the numbers that you computed. And I was also just wondering, like, what does reachability not give you that this technique offers?
So thank you for your question. So regarding iOS reachability, we also had that included. The thing was that we wanted a fair comparison between having the whole screen available, so all targets available for the user. We actually did a study with the reachability technique, so I have the data, so we can talk about it offline if you're interested in that, so that you have a comparison for that. And what does ForceRay not allow you is just what I said. It's like if you go beyond touch input, like simply tapping, that's nothing that would work with ForceRay, for example. So let's say you want to swipe something at the top, that just wouldn't work. So what we think here, what we could do is, for example, use a different force selection technique, like a dwell time. So you wait for 1 second, and that would activate a gesture mode, and then you could do something like a thumb rolling or something to do a remote swiping, for example.
Hi, this is Mingrui Zhang from University of Washington. A really neat presentation. I love it. But I have a question. So people use shrink mode a lot because they preserve the whole. It not only preserve the whole screen, but also enable every kind of gesture input. So you can double tap, you can swipe. But for like techniques like bezel swipe, ForceRay, there is only one dimension where you can drop and then release. I wonder, like for example, like double tap. How do you have any idea to extend this kind of technique to those like more dimension?
Yeah, as I just mentioned, so what we could do is do a different selection mechanism. So in force input, there are different ways of confirming the input. So the quick thumb lifting could be used for the tapping, but if you could also use a dwell time from 1 second, you could enter a different mode at that point, and then a lift-off could, for example, mean a double tap. But I think from a usability perspective, that would be very complicated. So I think then maybe other things like also enabling back-of-device interaction could be something, or squeezing of the device. That's something that would need to be carefully investigated. So that's a clear limitation of ForceRay. And yes, it's true that with the shrink mode you can do all these things. But nevertheless, what is a little bit sad about the shrink mode then is we have this big screen and we can't then fully make use of that. So that was the intention of ForceRay, to keep everything in the scale, but it's a clear limitation at this point.
Okay, we have a little bit of time for questions. I can ask one just now while anyone else in the audience can think of another short one. So I guess there's kind of maybe two parts to this, but I'll ask the first bit first. I may have missed it. Do you have a sense of how often the participants you used actually use their device one-handed?
So we don't have complete statistics. There are a lot of papers that basically quote that people use the device one-handed. So we didn't conduct a separate study on this, but we basically based on that. So it's also by observation you see that there's often situations where people like to use it one-handed, but at some point they also see that the device is too big, so they start using the second hand. I also observed that in here at Kai, we were demonstrating ForceRay in the hot booth, and some people were still using the second hand. So I think there is a demand for that, for the one-handed use, but at some point the devices are just too big for their hands, so that they automatically stick to using a supportive hand at the same point. But there is a lot of evidence that people would prefer to use it one-handed, but the question is if they can actually do it one-handed.
Cool. And then just quickly with the second part then, did anyone report any difficulties using the force with the one-handed approach? Yeah, sure. So force input is nothing that you can learn very quickly. And at the first point, people say, oh, this is super sensitive. I just applied a little bit of pressure and the ray is already at the end, or the cursor is already at the end of the ray. And that also depends a little bit on the pressure space that you have in your device. So we used an iPhone here that comes with a pressure-sensitive screen, and it has about 4 newtons of pressure range. But if you use a standard force-sensing resistor, they give you, for example, 10 newtons, which at some point is also difficult to control because it becomes tedious the more force you have to apply. But it would make things easier. So
And we also added a filtering technique, a €1 filter, to get a little bit out of this very sensitive feedback that people got. But that's what they basically said. It was difficult to get used to this.
Okay, thank you. I think the last question is going to have to be offline, unfortunately, just for time. So let's thank